Okay. So let me tell you what Hayabusa-2 has been doing when it was staying at Ryugu. It arrived at Ryugu about a year ago, and then it's been such an exciting year since last June. But anyway, let me start with why we are doing this. Why we are doing this sample return mission. Well, the target object of Hayabusa-2 is Ryugu. It's a primordial asteroid. It's a small body born outside the snow line. Oops. It's not a, there's a pointer. Oh, here it is. Okay. So born outside the snow line. Earth was born dry because it was born inside the snow line. So some small body born outside the snow line must have brought water to Earth. So that's why we care about these small bodies. And Ryugu, being a primordial asteroid, is one of those. Is a member of a category of small bodies who must have brought water to our planet to make our planet habitable. So I think understanding small bodies, primordial small bodies, is really central to planetary science. That's why we dare to send a sample return mission to Ryugu, which is the same with NASA OSIRIS-REx mission. So when we got to Ryugu about a year ago, June last year, we were shocked to see its unfriendly surface condition. And what I mean by unfriendly is something like this. I forgot what this. Well, we did expect to see boulders on the surface, of course, but the problem is that boulders are everywhere. We cannot find the spot that seems safe enough to land. And when I say arrival to Ryugu, what I mean is that we got to the home position. Home position is like 20 kilometers away from the asteroid and on this Ryugu Earth line, from which you can communicate with Earth very easily. But anyway, when we got there, and knowing that we have to come down to the surface someday to get the samples, and knowing that the surface features look like this, we're kind of shocked. Pre-launch design is that we can safely land on the surface if there is an area of 100-meter diameter that doesn't have boulders larger than 50 centimeters in size. And the size of the Ryugu is like 1 kilometer from here to here. So a circle like this size that is free of boulders larger than 50 centimeters, that's what we thought would be existing. And don't ask me why we thought so. Well, yeah, I can explain why we thought so. Because we had Hayabusa first, that went to Itokawa. Itokawa did have such a big friendly area, but that wasn't the case for Ryugu, which was shocking to us. But it shouldn't have been shocking, but anyway, I'll come back to that point later. So what we worry is, of course, we have to come down to the surface. It's a sample return mission. The tip of the sampler horn must touch the surface without any other part of the spacecraft being hit by those boulders on the surface. And the length of the sample horn is 1 meter, and that's where the 50 centimeter criteria comes from. 1 meter size sampler horn, so taking the safety factor into account, boulders larger than 50 centimeters shouldn't be in the landing ellipse. And then the size of the landing ellipse, pre-launch number was 100-meter diameter. So that was the situation just about a year ago. But there was no time to lose, so we kept on studying the surface and come to identify that this would be the safest spot on the surface, 100 meter times 100 meters square. And at the same time, what was really good about Hayabusa-2 is that we did have small robots from Japan as well as from Europe on board. So by September last year, we're not ready to send the main spacecraft to the surface. But we thought we could ask these guys to take the risk and give us some information what the surface looks like. And that operation of the small robots were performed last September and October, which happened to be really, really successful. So we sent this Minerva 2 from Japan to the surface. Well, actually, it's really a small robot. The size of this robot is like 10 centimeters from here to here. But, and this guy can hop on the surface under the microgravity environment. So it can land on the surface, take an image, and then hop to another spot and take the image. And that performance was done perfectly and gave us crucial information about the surface condition. which was also true for the case of the European lander. It's a Mascot by the name Mascot. It's a shoebox size lander, and it weighs like 8.7 kilograms. Again, we deploy this from the altitude of like 64 meters above the surface, and then let it touch down on the ground and get settled to give us some information of what the surface condition is like. And this, again, this happened to be really, very successful. And at the same time, we made some changes in the plan. First of all, pre-launch design is that the navigation accuracy is like 100 meters times 100 meters, which means that you don't know in which spot within this square you're going to be landing. And we did identify the safest spot on Ryugu, which is this 100 meter times 100 meter times 100 meter square. But if you say that I don't know where we're going to land within this square, there's a chance, not a negligible chance of hitting this big rock here, big rock here, big rock here. So we did move on with this we did move on by identifying this safest spot on the surface. But if we keep saying that size of the landing ellipse is 100 meters, I think we would be, stalled somewhere. So instead of moving forward, knowing that we were not going to move, we will not be able to move forward anymore. Instead, the team was determined to say that we would improve the accuracy of navigation down to 20 meter. So identify a 20 meter diameter circle here, which seems to be free of big boulders. So now we did identify the spot, although the size is smaller by a factor of 5. And then the issue is that you have to improve the accuracy of your spacecraft navigation by a factor of 5. And this decision was made October last year, 4 months after the arrival to the asteroid. And as I said, this number is the pre-launch design, and this 20 meter, this new number is coming from the information you get after arrival to your destination. So this is not an easy situation. And naturally, the team changed the plan from the original one. Originally, we thought that the first touchdown would be made at the end of October. Then there will be 3 touchdowns. And the last one will be utilizing a new technology, new technique. So we thought that things would be rather easy. That's why we dared to put such a optimistic plan. But instead, of course, the team naturally changed the original plan to something like this. They said that they will postpone the first touchdown to early 2019. And because of the necessity of improving the landing accuracy by a factor of 5, they have determined to introduce this pinpoint landing technique, which was supposed to be performed for kind of fun, for the fun of it. But instead, now that it seems necessary to improve the landing accuracy, now we're going to introduce this pinpoint landing technique from the first touchdown. And even though this announcement is really about the delay in the mission, a pleasant surprise was none of the media people complained about this, and that's when we thought that the Hayabusa-2 is really a beloved mission. So the change in the plan, introducing a new technology, the target marker, or I should have, can I go back? Okay. I should have mentioned what this new technology is like. So this pinpoint landing technique, it's going to be utilizing a device by the name target marker. It's like a mirror ball. And if you place this on the surface of Ryugu, and if you flash, these guys become super luminous. These guys looks like a very bright spot on the surface. So it's like a lighthouse. And by referring to it, you can navigate you never miss it, and you can navigate your spacecraft very correctly. So placing the target marker in the right place is one of the critical issues. But what happened is that it wasn't in the right place. So we have identified this 20-meter diameter circle, which looks to be very, very safe. So we had determined ourselves that we're going to land in some way in this area. So the target marker should have been inside the circle, but instead it was located here. So what happened is that something like this. This is the way we thought we were going to land. Target marker wasn't in the super right place, but in kind of a in the intermediate place. The distance from the center of this target to the target marker is like 17 meters, which is not small. So the team analyzed the situation and have to identify a small circle here, a smaller circle here. Radius is 6 meters, and thought that this could be the one instead of this one. So you have a large circle farther away from the target marker, smaller circle closer to the target marker. And when I say small, how small it is this place. I said its radius is 6 meters, which means that the radius is just like the size of the spacecraft itself. So what would you do? Suppose you were in the project manager's position. How would you make your decision? And to my surprise, at least, they have decided to go for this area instead, not this original area, original target. And of course, they did make a trade-off discussion, but as I listened to them, I thought that they were so sure that they can make it to this area. So that's why they said they want to go for this. And it also tells you that it's not the size of the landing ellipse, but it's more the distance to the target marker that matters more. And then, so everything was ready, and then on that day, what happened is the 5-hour delay in the start of the descent. It was supposed to start at 8 o'clock in the morning, but one of the operators didn't wake up. No, that's not true. Because of some complicated combination of the parameters, it didn't start. But then the team decided 5 hours later we can do this by speeding up the descent speed. The nominal trajectory was like this. Oh, here's the time versus altitude. The nominal trajectory was like descending at 40 centimeters per second, but instead you can speed up, then catch up with the original plan, and then beyond that, you can just follow the plan. So that decision was made on that morning, which is a kind of another pleasant surprise. Well, it wasn't really pleasant, but still. Now that I can say it was a pleasant surprise. And then on that, can you play the movie, please? Then now the spacecraft is at 8.5 meters above the surface, staring at the target marker situated here, making sure that the spacecraft is in the right position, because after this, the spacecraft will make just a free fall onto the surface. And now it has convinced itself that it's in the right position, so it started the final leg of the descent, the free fall to the surface. And then, we did touch on the surface. Everything went, thank you. Well, I have to tell you, there's something more exciting, later, but still, thank you very much. So everything went as we planned, which is shown in this computer graphics. Can you play this again? Can you play this? Yes. So, computer graphics is boring compared to the real images, but still. It tells you what happens. So when the sample horn touches the surface, a signal is sent to the spacecraft, so we shoot the bullet. And under the microgravity condition, the debris will go into the sample container inside the spacecraft. Everything went as planned, so we should be getting a good amount of samples, which is like 100 milligrams nominal, 1 gram maximum, so somewhere between 0.1 or 1 gram-ish, which is a huge amount for the modern analysis technologies. And now, so that's what happened in February, but we kept on we kept on challenging because, Brian May seems to like us because we keep on challenging. The next challenge that happened is the impact experiment in April. So what is the impact experiment? We deploy the impactor 500 meters above the surface, and then the main spacecraft itself will evacuate into the safety zone like this. But during this evacuation, the main spacecraft also deploy a witness camera, a detached camera. And then the trigger will put this impactor into a bullet which hit the surface to create an artificial crater on the surface. It sounds like a very complicated operation, but everything worked well. Deployment, precise deployment of the impactor, precise deployment of the detached camera. So that made us see the impact that made us record the impact experiment like this. So 2 seconds after the trigger, you can see the debris coating forming on the surface, and then that continued for 25 seconds at least, and indeed it continued for about a minute. And then what about the crater? What does the crater look like? 2 weeks later, when it was safe to go back and take the image of the surface, Hayabusa-2 went back to that spot and to take the image like this. This is like before and after, so you can clearly see that there's a dark marker on the surface, which should be the signature of the crater. And the size of this crater is like a 10-meter diameter, which is a bit larger than what the scaling law tells you. So what we are learning from here is something really, what we're getting here is some really new insight into the formation mechanism of crater under microgravity. So this impact experiment really went well. And this impact experiment is to form an artificial crater so that we can study the crater formation mechanism under microgravity. This is the primary objective. But there's another objective, and that is to excavate the unweathered surface material. Unweathered subsurface material for sampling from the surface. Once you make a crater, you eject the subsurface material onto the surface. They are piling on the surface. So if you get to that piled up subsurface material, piled up material ejected from the subsurface, I think that's a smart way of getting the subsurface material. So in order to do that, you have to go down to the area close to the crater. But the argument is, of course, the natural argument is, of course, especially for those people above me, is that why do you take the risk? We have paid all those efforts to make the first touchdown successful, and why do you tell me that you have to go back there again? But the argument is that the target of the impact was situated at this position. The team was smart enough to do so, because if you do so, it's on the edge of this rather flat area, which had been confirmed to be safe to touch down and take the samples. And the team was smart enough not to put this target at the central part of this flat area, because that may jeopardize the favorable condition of the area. So instead, they thought that they can hit here, and the ejected particles will be piling up on this flat area. So if we go back to this flat area, we can get the subsurface materials. And instead, well, if you think about how complicated this impact experiment is, it's kind of amazing. But there was an error in the impact by 20 meters. So the actual crater was formed here. But still, it's rather close to this safe spot, which had been confirmed to be safe to land and get the sample. So the natural choice, including the time pressure, we have to complete everything before late July. So including that time pressure, at mid-May, when they were thinking about this, they thought that coming down to this area and get the sample, touching down on this area, would be the most reasonable way of getting the sample, subsurface materials ejected by this impact experiment. So that was the decision made around mid-May. But what happened is that, so that decision naturally led the team to perform a dropping of the target marker into that promising area, which we call S01, but to that promising area. But what happened is that there was an anomaly detected during this operation. So, so the operation was aborted. No damage to the spacecraft. Of course, that's why we let the operation to abort. But anyway, no damage to the spacecraft. The situation was analyzed, and we know what happened. But still, that really escalated the pressure to stay safe and don't go for the second touchdown. And the pressure not to do the second touchdown was elevating by this time. So that was like mid-May or late May. But what was kind of funny, I can say it's funny now, but still, what was funny is that in the images acquired during the ascent after the abort, a more attractive area was identified. We were supposed to be going to, this is the center of the crater, and this is the area that had been confirmed to be safe, and to which target marker was supposed to be dropped, but didn't. And during the ascent from this, from the operation, they did look at this area here and confirm that these areas are kind of, well, at least this area is kind of safe to go. And besides, we thanks to that detached camera which witnessed the impact experiment, we had known that ejector materials were ejected asymmetrically. More ejected materials on this side than on this side. So the natural argument is that we should go for this. But time is pressing. And because now you have identified a new spot, you have to go through this process all over again, like a detailed analysis of the area. And you have to place the target marker in the good position and others. While there's a pressure from above that, things start going zigzag, and some people don't like it. Of course, if I were in that position, I would say the same, but And more fundamentally, why should you take the risk for the second touchdown? We got the sample already. Why do you do this? So it was kind of an interesting exercise, going on for about a month and a half. And then under this pressure, the team has shifted the target position for the second touchdown, completed all the pre-second touchdown descent operations perfectly, and studied numerous cases to be convinced that there's only acceptably small risk, acceptably minimized risk of losing the spacecraft. And that should be ready for us to go to the second touchdown. So this is it. It's this 7-meter diameter circle. And this time, target marker is within the circle, so looks easier than the first touchdown. Nice location, nice localized, nice placement. Nice placement of target marker, and the size of the landing ellipse is a little bit larger than the first touchdown. So we did kind of anticipated this, but it did. Second touchdown completed perfectly. Yeah, and by the way, I think you guys are one of the first on this planet to watch this video. So, we did get the second touchdown. That was for the subsurface material, but I think it had a broader implication. And if you guys are thinking, wow, you wish to be a part of such an exciting mission, I think that was worth of it. And I think we will continue to take this style. We keep on challenging. Thank you very much.
Wow. An amazing, amazing mission. Can we give him another hand for how successful? Just incredible. It shows how lucky we now are to be partners with you, Masaki. So we look forward to a lot of neat things in the future. So we have time for a couple of questions, 2 or 3 questions, if you'd like.
Is there a prize for a storyteller as well?
Yes. Thank you, Brian. Brian O'Brien just said, is there a prize for a storyteller? And I think that Masaki wins this.
Well, I think the story itself is great. And,
yeah.
Yeah.
And I do like the Queen references, by the way. So any questions for Masaki? Well, you'll have an opportunity to hear from him. Mahesh.
Hi, great one. Just two really curiosity rather than question. When you said that the decision was made to speed up the descent, how much time did you have in terms of time delay where the spacecraft was when the decision was made, and then when you sent this command and then the spacecraft had to change, IC speed, etc.?
Oh, so before we send the command, the spacecraft stayed in the home position. So relatively, it didn't move at all in that sense. But you have to come back to the original plan because the asteroid is rotating, and we have identified a spot, like longitude and latitude, where the target, where the landing spot should be. So we really have to catch up with the original plan. We couldn't just shift the plan. So we need to speed up the descent, and then. But on the other hand, the team has had to be making so many rehearsals. They have tried descending at this speed before. So in that sense, they have driven at this speed. So it wasn't the first time that they have ever driven at this speed. So, so many rehearsals behind the success of this operation.
Okay, and do I have time for the second one, or should we?
Go ahead, and then we have a couple other people.
So my second question, this probably is a question, is that after the impact, what surprises me is that the fresh surface that is visible actually is darker than the previous one.
Mm-hmm. So there are two explanations. Maybe the space weathering on the surface make it brighter. That's one idea. The other idea is that because the impact could have made smaller particles, and that could have reduced the albedo. But once we get the sample, we'll know the true answer. Yeah.
Did you have close control on what you were expecting in terms of maximum particle size that the collector could obtain?
There's a physical limit because of the way we do the sampling, like
Sure.
the size of the tube. And the maximum particles we can get is 1 millimeter.
Okay.
That's
Yeah.
that's the
But mostly in finer materials, I
Sure,
would think.
sure.
Yeah, thank you.
So when I look at meteoritic samples of asteroids, I oftentimes can see internal structures, brecciation, variations in albedo. In any of the high-resolution imaging that you had of the clasts and the boulders and the cobbles, did you see any structural information like that?
Yes, I don't know if I'm answering your question directly, but like the crater, when we made the crater, it looks darker. But how dark is it? It's like the darkest spot you see on other area. So I think we made a variation on surface by making the crater, but that variation is still within the range that was already observed before we made the crater. So crater made it darker, but that's not super dark. That's as dark as some darkest spot that was already existing on the surface. So the sample we will tell you where the variation on the surface is coming from. That's the current thinking.
Jake?
Yeah, Jake Bleacher, NASA. I was just wondering if the technology and the approaches you're using here, have you thought at all about applying this to lunar sample collection and possibly caching samples that could later be returned at some point?
Lunar, right? Gravity field is very different. So these things are really optimized for the microgravity conditions. So I don't think I can answer that question now. I'm skeptical, but still, I don't want to be,
Okay.
Yeah.
Just in general, the sample collection approach, do you think it might have any application to lunar sample collection? Maybe not the way your specific spacecraft hops, but.
For the lunar case, you don't do touch and go. You have to land because of the stronger gravity. If you land, why do you do this? Is this the best way of sampling? I don't think so. But again, I don't want to be too negative. So yeah.
Okay, just one last quick question.
Real quick question. Would it be safe to say that space weathering is turning out to be, on primitive asteroids, is turning out to be more complex than we expected? Because initially you thought that things were getting redder with space weathering, and redder and darker, but now the crater seems to have been darker. We don't know the color yet, but it seems like we're having somewhat contradictory indications of which way space weathering is going.
Yeah, space weather on S-type asteroid make it darker, but there's some experimental, well, there's I think a paper saying that space weathering on C-type asteroid make it brighter. So yeah, but that's what the literature says. And well, again, we will learn when we get the samples.
Okay, great. Thanks, Masaki.